Okay. A very good morning to all of you. Today we will discuss the experiment number 1, that is the determination of coefficient of velocity, coefficient of contraction, and coefficient of discharge for an orifice. We have already discussed the rest 3 experiments in details, and the corresponding videos have been uploaded in YouTube, and the links have been shared to you. So today we'll go ahead with this. The procedure will be same. This is the explanation of the experimental details together. I'll be giving you the theoretical details of or the theoretical background of this particular experiment, in addition to an insight that how the different parameters are to be measured experimentally. So this PowerPoint will be giving you both on theoretical insight and also experimental insight. So after going through this, you will be in a state to understand the experiment in details, both its theoretical and experimental aspects and details. Then there will be one more video which is explaining you purely the experimental mode of determination of these 3 parameters. Okay, so let's go ahead with this experiment one by one. So this is experiment number 1. So we'll start with the first thing is the aim of the experiment. So aim of the experiment is to determine the coefficient of velocity, coefficient of contraction, and coefficient of discharge of an orifice. Okay. So we'll discuss what an orifice, how it is different from a ventrimeter in the next slide. So here, first of all, let's try to know the experimental setup to be used for this purpose. We'll discuss this all these terms. What is this coefficient of velocity? What is coefficient of contraction? What is coefficient of velocity? And what is an orifice above all in details in the next slide to come. So first of all, aim of the experiment is here to determine coefficient of velocity, coefficient of contraction, and coefficient of discharge for an orifice. These are also called as hydraulic coefficients of an orifice. Okay. So as you know, let me just tell you one line about orifice. Orifice is an instrument which is being used to measure the flow rate through a pipe. Like ventrimeter, the same purpose. Ventrimeter is also being used to determine the discharge or the flow rate through a pipe. And the orifice also serves the same purpose. Okay. So the next point is apparatus required. So we need a setup. We need an experimental setup to determine these 3 coefficients and also a stopwatch. Right. So this is how the experimental setup looks like. It's called as the hydraulic coefficient determination through orifice setup. So these are the following components. Most of the components are similar, or most of the components are similar to the previous experimental setups what we have seen. So let's see one by one. First of all, is the pump to circulate the water. This is a water reservoir, as you know, which acts as a central reservoir of water from which the water is being circulated to pump for the circuit. Then you have got a water collection tank for experimental determination of the discharge. You know the discharge is being calculated. The actual discharge is being calculated through experimentally, like the volume or divided by time. So this tank is being used. You are already aware of that this kind of setup, this kind of tank is a common feature for almost all the experimental setups which you are discussing now. So this tank is being used to calculate the theoretical discharge, that is volume divided by time. So volume of water collected divided by time taken for collecting that amount of volume of water. So that ratio will be giving you the actual discharge. Okay, the next component is the discharge controlling valve, because the experiment is to be repeated for 3 different values of the discharges. So we'll be conducting the experiment for 3 different values of discharges. So this is the discharge controlling valve through which you can control the discharge which is maintained for a particular experimental reading. Okay. The next point is a water reservoir connected with an orifice for determination of the discharge coefficients. So you can see this one. This one is your, you can see my cursor. This one is your tank where you have an orifice attached over here. Okay. So you have got a special arrangement here. You can see here. This arrangement is being made for the purpose of determination of actual velocity. We'll discuss in details about this particular setup. Okay. Now the major thing is that there is an orifice over here, which I've tried to show you over here. This is the shape of the orifice. A plate with a hole. It's a very simple in construction as compared to the construction of a ventrimeter. Like the ventility, you have got a converging, a diverging, converging section, the cross section, a diverging section. As compared to that, an orifice is very simple in construction. It's just a plate with a hole. Okay. So this is the experimental setup. The first slide is clear, I hope. This is you are aware of the objectives of this experiment, and you are also aware of the experimental setup and its various components which is basically being used for determination of this hydraulic coefficients. Okay, coming to the next slide. Let's go for a little bit theoretical background of this orifice. First of all, we'll discuss about the difference between this orifice and a venturimeter. Okay, as I said, the purpose is same. Orifice and a venturimeter are being used for the same purpose. They are being used for calculation of flow through a pipe or discharge through a pipe. So then, why, in which cases we'll be using venturimeter and where we will be using orifice? That's a point to be discussed. So orifice is basically defined as a device which is used for measuring the rate of flow through a pipe. Orifice it is also called as an orifice plate. Okay. It serves the same purpose as a venturimeter. However, it has got the following advantages over the venturimeter. First thing, it is less costly and more flexible in operation, whereas venturimeter is costly because of its complicated and complex design. As you know, venturimeter is having a converging section, a torque, and a diverging section. So this complexity in design makes it costly. First point. The second point is venturimeter is expected to have more losses as compared to an orifice. Although both of them will be causing a pressure drop, and that pressure drop, drop in pressure is actually a parameter through which you can measure the flow rate through the pipe. But the amount of losses incurred in case of venturimeter is expected to be high as compared to an orifice. That's the second point of distinction. And the third point is orifice is basically preferred as compared to venturimeter for measurement of flow rate through small pipelines. For small pipelines, basically orifice is being preferred much, whereas venturimeter is preferred for larger volume of liquid and gases. So just one application point of trying to show you that how an orifice plate is being used and how venturimeter is being used. You could see that the orifice meter is an orifice meter. So this is an orifice plate or orifice, you can say. So and here you could see there is a venturimeter application point. So coming to the next slide, here we will try to know the constructional features of an orifice. It's very simple in construction. Orifice consists of one flat circular plate, and this circular plate will have a one circular sharp edge hole bored in it. The circular sharp edge hole is basically called as the orifice. Okay, somewhat looks like this. Okay. Diameter of the orifice is about 0.5 times the diameter of the pipeline in which you are going to incorporate this orifice. It may also vary from 0.8 to 0.4 to 0.8 times the diameter of the pipe in some special cases. Orifice is being installed in the pipeline with the two flanges of the pipe. You could see this here is a pipeline. The left hand side is a pipeline. The right hand side is another pipeline. They are being connected to a flange coupling system, which is a flange. This outward protruding section is a flange. So in between these two flanges, your orifice is being inserted. You could see. So because of this the insertion of the orifice, the streamlines are getting bent, and gradually they are getting converged. And at a particular cross section, they are achieving a minimum cross sectional area. You only know that this section where they achieve the minimum cross sectional area is known as vena contracta. Because I presume that you have already been covered. You've already been aware of this term. Still, we'll be touching the basics, of course, in this particular discussion. So, orifice is installed in between two flanges of the pipe. That is what I've shown in this particular figure. Okay, fine. Next one. So, orifice will restrict the flow of fluid and will reduce the cross-sectional area of the flow passage. Orifice will restrict the flow of fluid and to reduce the cross-sectional area of the flow passage. Of course, because of that, a differential pressure will be developed across the orifice plate due to creation of pressure difference. Due to this creation of pressure difference, we will be able to determine the rate of fluid flow through that particular pipe where you are going to insert this orifice. This is the basic parameter. You know that in case of venturimeter also, that venturimeter is going to cause a pressure difference because of its constructional features. Similarly, an orifice is also going to do the same thing. It is going to lead some pressure difference, and that drop in pressure, that difference in pressure is going to be used as a parameter for determination of the flow velocity or the flow rate to the pipeline. Okay, this is the constructional feature and how does it cause the pressure difference. Fine. Coming to the next slide. Okay, next point is let's discuss the three parameters one by one, which we want to discuss. That is the coefficient of velocity, then coefficient of contraction, then coefficient of discharge. So let's discuss these three parameters one by one. First point is determination of coefficient of velocity. Coefficient of velocity represented by CV. Please remember that this coefficient of velocity for an orifice is defined as the ratio of actual velocity of the orifice to the theoretical velocity through the orifice. It is the ratio of two terms, actual velocity to the theoretical velocity. Remember the term actual. So remember this term actual refers to the cross section of corresponding to the vena contracta. The term actual refers to the cross section corresponding to vena contracta, and the term theoretical corresponds to the cross section of the orifice. Remember, actual and theoretical. So actual refers to vena contracta, and your theoretical term refers to the orifice. Okay, if you see there are two diameters. You have a diameter of the orifice. You have got the orifice. You have got a diameter of the vena contracta, where the cross-sectional area is going to be minimum because of convergence of the streamlines. So that ratio. So coefficient of velocity CV is the ratio of the actual velocity to the theoretical velocity. That indicates velocity corresponding to vena contracta to the velocity corresponding velocity of the flow corresponding to the orifice. Fine. So this two ratio is actually called as your coefficient of velocity CV. So let's see how can we determine this coefficient of velocity experimentally. Fine. So fine. So let's discuss the theoretical velocity first. That is the velocity through orifice. As I said, theoretical term indicates the velocity through the orifice, and the actual indicates the velocity through the vena contracta. So theoretical velocity first of all represented by V subscript CO or VO. Okay, fine. So let's try to find out what is the velocity of the streamline at the orifice. So let's consider a tank with an orifice attached to it for the measurement of the flow rate. So this is a tank. This tank is similar to the tank or the setup which we are using in our fluid mechanics laboratory. So there is a tank, and in this tank you could see there is an orifice. Orifice is just you can see it's just a plate with a small hole. Okay, so it's just an opening through which the water can come out. So so this is an orifice. This is a tank. Besides that, you have got a small opening. So that opening is nothing but an orifice. Okay, so let's try. Our purpose is to find out the velocity of flow. Velocity of the flow at the orifice. Okay, fine. So I will discuss this figure one point by point. There are many details being given over here, which I will be discussing point by point. Okay, so next point. The orifice meter converges the streamlines due to its small cross-sectional area. As a result, the streamlines at a minimum cross-sectional area at a certain distance from the orifice called as the vena contracta. You are already aware of this. So that is what I have tried to show you over here. Here you could see this one is my orifice. OO section is my orifice section. So your streamlines are getting converged. So they are attaining a minimum cross-sectional area a certain distance from the orifice, and that section is your 2-2 section. So that refers to the vena contracta section. Right? So OO refers to your orifice section, and 2-2 refers to the vena contracta section, where the cross-sectional area is cross-sectional area of the streamline is achieved to be attained to the minimum possible. Okay. Now let's apply Bernoulli's theorem to two cross sections, cross section 1,1 and cross section 0,0. So cross section 1,1 corresponds to a point. You could see here, cross section 1,1 corresponds to a point inside the tank along the center line of the orifice, and the point 0,0 is the cross section corresponding to the orifice. Exactly. There. Okay. So you can assume that through this 1 point and this 0 point, 1 point is inside the tank and 2 point is inside is at the center of the orifice. So and both of them are along the center line of the orifice, right? So let me apply the Bernoulli's theorem. That is the total energy head at both these points are constant. Okay, and that negating the losses. If I apply Bernoulli's theorem, so my equation will be this one: P1 by rho g, the pressure head plus velocity head plus datum head at the point 1 is equal to the total head at the point O. Fine. So now you could see that both these points, as both the points 1,1 on the section 1,1 and the section 0,0 and the, are correspondingly are at the same datum level from the bottom of the tank. So I can neglect the datum related point, that is y1, y0 can be neglected. To be leading to this expression. Now the second assumption, the second point to be considered over here is that cross-sectional area corresponding to the section 1,1 is very high or very larger as compared to the cross-section corresponding to the section 0,0. Section 0,0 corresponds to the cross-sectional area of the orifice, whereas at the section 1,1 the cross-sectional area is comparatively high. That is why velocity corresponding to the cross-section 1,1 will be very less as compared to the velocity of flow corresponding to the cross-section 0,0. I think you can understand that this is clearly as per equation of continuity, A1 V1 is equal to A2 V2. So based upon that, we can clearly say that velocity corresponding to section 1,1 will be very less as compared to velocity corresponding to the 0,0 surface, 0,0 section, that is the section corresponding to the orifice. So we can clearly neglect this velocity term corresponding to the section 1,1. Accordingly, this V1 square by 2g term that we can neglect. So P1 by rho g is equal to P0 by rho g plus P0 square by 2g. Fine. Now, the last point which you can consider, if we consider that at the point 0,0, the water is coming out of the orifice, so it is going to be it is almost in contact to the atmosphere. So the pressure at the point 0 will be almost atmospheric pressure, and that is why, whereas the pressure at the point 1 will be the hydrostatic pressure. Fine. That is why if you compare these two pressures, pressure corresponding to the orifice O or the section 0,0 is expected to be less as compared to the hydrostatic pressure. That is why this EO by rho g term can also be neglected, and yes, I can also negate this term. Then in that case, I will have one thing, P1 by rho g is equal to V0 square by 2g. So this P1 by rho g is nothing but the height h. Okay, so I can write down. So from that we'll be getting this V0 is equal to 2gh square root. So this is my expression for the velocity corresponding to the orifice. Okay, so that is called as my theoretical velocity, because as I said, the term theoretical indicates velocity theoretical indicates corresponding to the term theoretical corresponds to the orifice. That's why I got this V0 is the velocity of the flow at the orifice is 2gh square root. Fine. I got the theoretical velocity. Now I need the actual velocity. Remember, actual velocity means the velocity corresponding to velocity of the flow corresponding to the Vina contractor. So in order to find out that actual velocity V actual, or that is the velocity of the Vina contractor represented to be V2. So that is being found out experimentally through a setup like this. See, this is the tank. Through that, this is the through the orifice you are having the flow of water. The water is getting discharged, and the streamline of the water will be coming in the form of parabola. It's already known to you. So if we try to find out the locus of this parabola, okay, any point on the parabolic streamline coming out of the orifice will have two velocity components. One is the horizontal component, one is the vertical component. I've shown that the horizontal component is x is equal to dt, and the vertical component will be half gt square, because vertically it is coming because the parabola is actually the parabolic locus is actually or parabolic profile is actually a combination of two things: motion of the gravity and the linear motion, linear motion. So it's a combination of both of this. So at any point, there will be two components of velocity. One is the rectilinear component, one is the vertical component. So that I've shown, x is equal to vt and y is equal to half gt square. So if I represent that and try to find out the expression for the velocity, then this v will be coming to be g square by 2y. That means velocity, this v is nothing but our actual velocity. Okay, that is what we are trying to measure experimentally. So x is equal to vt by half gt square. If I replace t by x by v, I get this. So v will be coming to be g square by 2y square root. Fine. This will be given by the actual velocity. V actually equals g square by 2y. Okay, so this will be getting how? This will be getting laboratory through the experimental setup. We have got a setup which I will show you now. So if I get V actual, then my coefficient of velocity CV will be the ratio of the actual velocity to the fluid velocity. So V actual by V theoretical, that is equal to V2 by V naught. It's coming to be CV is equal to x square by 4yh. So you could see that you just need, if I want to calculate CV, because in this experiment I have to find out three things. One is the coefficient of velocity, one is coefficient of contraction, and one is coefficient of discharge. So this is coefficient of velocity, the first hydraulic coefficient CV. So to calculate this CV, I just need x, y, and h. So x and y are nothing but the location of a point or the coordinates of a point on the streamline which is coming out of the orifice. So this x and y will be obtained from the experimental setup itself. Okay, and the term h is nothing but that height of the water which is maintained in the tank. Okay, so to experiment in the experiment, we have to if I want to find out CV, I just need to have three values. One is the height of the water that is maintained in the tank, and then for that height you will be you will have a water jet coming out of the orifice. So this streamline I have got a setup to which I can just concentrate on my point. So the corresponding x and y locations I can get it. So x, y, and h if I get, then by putting in this formula, I can get the value of the coefficient of velocity. So this is the setup. Yeah, this setup what I was talking about. You could see this h I have shown here. H is the height. Okay. So height from the level of the orifice. So that I have shown you, y2 minus y1. This is the level indicator. So I can measure it experimentally, and you could see this setup. This is the point, and here I am trying to find out this x and y. This is the scale. You could see there is a horizontal scale, there is a vertical scale. So the measurement over this horizontal scale and vertical scale means there is a pointer. You can see there is a pointer. This pointer you have to take this point. This one can this particular vertical scale. What you can see, this is movable over this horizontal scale. So you have to take this pointer and point on the streamline at a specific point, so that it will just touch the streamline. Then this yellow line is actually indicating the streamline coming out of the orifice. Then for that location, you have to find out the value of this x and y on the scale. So you have got a vertical scale and horizontal scale, and that will be giving you the values of x and y. So this x and y will be getting over here. You have to put over here. This h will be getting over here. If you get this three things, you can get the value of the CV. Okay, so that is how you get the value of the coefficient of velocity. Now coming to the second one, that is determination of coefficient of contraction. Okay, again this is the ratio of the actual area of cross section to the theoretical area of cross section. Again I'm emphasizing of the same term, same thing again. Now the term actual is again implicating your vena contracta, and the theoretical term is indicating your orifice. So coefficient of contraction will be the ratio of the area of cross section corresponding to the vena contracta to the area of cross section corresponding to the orifice. So the ratio of these two will be giving the coefficient of contraction. So if I define it mathematically, it will be represented by a term called C subscript C, given by A vena contracta by A orifice. So is equal to, as you know, in this particular analysis, the notations what are used. Area of the vena contracta has been shown by A subscript 2, and area of the orifice has been shown by A subscript 4. So CC is equal to A2 by A0. Okay. What we have this A0. Area of cross section of the orifice is known to us, but we are not aware of the area of cross section at the vena contracta. It's also difficult to exactly measure that the area of cross section of the vena contracta. That is why we won't be calculating this CC directly. We'll be calculating CC indirectly. Okay, and how indirectly? I'll tell you in the next slide. So for the timing, I've just defined CC, but I'm not going to calculate CC now. The difficulty I've told you, because cross sectional area of the orifice is known to me, but the cross section of the vena contracta is not known to me. That is why I'm not calculating directly, but indirectly. So that will be showing you the next slide. I hope this slide is clear. Coming to the next slide. Third point, that is determination of the coefficient of discharge, C subscript D. So coefficient of discharge is again the same thing. We define it like this. It is a term which is the ratio of the actual discharge to the theoretical discharge. Okay, actual discharge to the theoretical discharge. So actual discharge, it is the ratio of the actual discharge and the discharge to the vena contracta to the theoretical discharge and the discharge to the orifice. Okay. Actual discharge is the discharge measured through the vena contracta, that is area cross section of the vena contracta into velocity of flow through the vena contracta, A2 into V2. Similarly, theoretical discharge is the discharge measured through the orifice is equal to area cross section of the orifice into velocity of the orifice, A0 into V0. Okay. So if I go for the ratio CD is equal to Q actual by Q theoretical is equal to A2 into V2 divided by A0 into V0. So that will be ultimately coming to be A2 by A0 into V2 by V0. So this A2 CD is equal to how much? You have CD is equal to how much? A2 by A0 is nothing but the coefficient of contraction CC into V2 by V0 is what your CD. Okay. So please remember here, it's a very important relationship that your coefficient of discharge is actually a multiplication of coefficient of contraction and coefficient of velocity. Right? That is why, as I said, that coefficient of contraction we will not be finding out directly, but we will be finding out indirectly. How? We already got the value of CD, that is coefficient of velocity. Now we'll be finding out the value of CD experimentally. Okay. Once we got the value of CD and CD, then CC will be calculating by the ratio of this. CC will be CD by CD. That is how we'll be calculating CC. Right? So CD we calculated first. Now we're going to CD, and after getting these two, then we'll be going for CC as a ratio of these two. So let's see how to get the CD. Okay. Now CD, here we have got the expression for the theoretical discharge. There won't be any problem because we know the cross sectional area of the orifice. A0 is known to us. Also V0 is known to us. So there won't be any confusion about this. The only thing is the actual discharge. So actual discharge will be finding out how by the same conventional method that the volume of water collected divided by time. Because that is how we calculate the actual discharge. In the last experiment also you could have seen, in the experiment also, we did it like this. The actual discharge was found out by there's a collecting tank, and we allowed this collecting tank to get filled up to a certain height. What is the time taken for that height? We record through here from the stopwatch. So this time into the volume of this tank, this cross-sectional area is known to us, into the height of water collected is also known to us. So cross-sectional area of this collecting tank into this height will be giving you the volume divided by time will be the your total it will be giving the actual discharge. So actual discharge will be volume divided by time. So theoretical discharge is also known to you, A0 into V0. So your ultimately your CD will be Q actual by Q theoretical. So there's nothing, no confusion about that. So to find out this CD also, what you need this volume of the water collected, means again you need a height. The cross section area of the collecting tank is known to you. So height of the water collected, that you need to collect experimentally. The time taken to fill up that tank you need to find experimentally. and h is the height of the height of the water in that tank in which your orifice is being connected. That is already a known parameter to you. Okay. So in addition to the last in case of CV, I told you three parameters you need: x, y, and h. In addition to that, you need two things over here. One is that volume of the water collected, means height of the water collected in the collecting tank, and the time taken for that. Okay. इसका मतलब in one particular for a particular head for a particular discharge, your experiment you have to conduct the experiment for what? 3 times for 3 different discharges. First of all, you make the system on and you set a particular discharge, say T1. Take discharge, you have set the discharge. For that particular discharge, now your tank, the tank in which your orifice is being connected. So that tank will be a particular height of water. So that H you measure, and now there will be a streamline coming out. So you point that pointer over the streamline point, get the values of x and y. Then you go to the collecting tank and you measure the value of this height of water collected and time taken for that. So that means ultimately how many parameters you are taking? 5 parameters: x, y, then height of the water collected, then in the collecting tank what is the height of the water collected. That height is the height of the water in the orifice in the tank with the orifice. Then this height is the height of the water collected, the time taken for that. Total 5 things you are actually collecting. You are actually taking from one experiment. Okay. Hope it's not confusing. Fine. So we got CD. So once we got CD, as you know, once we got CD, now CC will be CD divided by CD. Okay. Once you got CD and CD, your CC will be CD divided by CD. So we got the 3 parameters. I think it is clear. So one observation table, because I'm not able to conduct the experiment, so I've just taken a reference of one of the seniors. You could see the area of the orifice is known to you. In the setup, the area of the orifice is known. Okay. We have done it for 2 types of orifice. One is rectangular and one is circular. Anyway, you will be doing it for say circular orifice. Diameter of the orifice is 1 centimeter is known to you, so cross area will be known to you. Area of cross section of tank is known to you. Then here you could see the data. You could see observation table. You see, I was talking about the parameters which we will be taking. You see, these are 3 different. You could see 1, 2, 3 indicate 3 different discharges. For that, this H indicates the height of the water in the tank in which your orifice has been installed. Okay, this is the height H. Okay, now this X and Y are the coordinates of the streamline which will be used for calculating the CV, X and Y. Yes, this is X and this is Y. Okay, here CV is being calculated. And then this is the time taken for filling of the collecting tank up to certain height. Okay, and this is a Q actual. This is your Q theoretical. Then CD and CC. Fine. Similar procedure. Once you get the values of these 3 hydraulic coefficients for 3 different headings or 3 different discharges, then you just have to get a mean of this, and you have to report that the mean value of the coefficient of velocity, coefficient of contraction, and coefficient of discharge is how much. Okay, this is all about the details of the theory and a view or a sense or a feel of the experiment, how you will get this data experimentally. And in the next video, we'll see that how in the experimental setup, how to get these data on a field. Thank you. Thanks a lot.